Hi, I'm Zor. Welcome to Unizor Education. I would like to introduce the operation of multiplication of matrices. Well, this operation is probably the most important operation on matrices. Yes, we were talking about addition of matrices and multiplication by a scalar, but this is actually where the whole theory is really flourishing, with multiplication. Why? Well, primarily because we have devised the multiplication in such a way that it actually represents the consecutive transformation of the space, transformation of the vectors in the space. So, if you remember, we have introduced matrices as just a convenient way to show how one particular vector is transformed into another. Now, let's just give you an example. For instance, we have a two-dimensional vector u, which has two coordinates u1 and u2, and we have the following transformation of the coordinates. Now, this is a linear transformation of the coordinates of the vector. Now, linear obviously because this is just a multiplication by a constant. So we are transforming vector u into vector v with coordinates v1, v2 according to these rules. And the matrix of transformation was actually just a table with coefficients. So far it's nothing but symbolics, nothing but a symbolic representation of these two equations. Well, obviously, if our dimension is 3, there will be 3 equations, etc. Now, the multiplication of matrix is something which allows us to write it in the following form. Either this form or this form, depending on certain conditions which I will talk later. So, transformation is equated with multiplication by a matrix. Now, that was the original purpose actually of the operation of transformation. But we have to define it in a certain way which is really kind of reflecting this type of thing. Now, more than that, I would like to define this transformation in such a way that if I have, let's say, two transformations, u to v and then v to w, one is represented by the matrix A and another is represented by a matrix B, then the transformation from u to w is a multiplication, a product of two matrices A and B. So that's the whole purpose, to build this matrix arithmetic in such a way that it reflects the processes of transformation. Well, that's the purpose. Question is how to achieve this purpose. And that's what we will be talking about in this and the following lectures. Now, this lecture is just an introduction. It's just to show you how the matrix actually transforms different vectors. Now, in the subsequent lectures, I will be spending more time defining different kinds of multiplication of matrices, and then the whole picture will become much clearer. So, multiplication of matrices in general is, well, it's an operation which takes two operands, two matrices, producing the third operand, producing the result, basically, the third matrix. Now, I was just talking about transformation of vectors using matrices. And now I just mentioned that matrix multiplication is operations into matrices. But, well, look at it this way. Any vector can be actually viewed as a matrix. In this case, it's matrix which has one row and two columns. Or I can write this way, in which it's two rows and one column. This, by the way, is called row vector. And this is called column vector. These are both vectors, but it's just a representation in a more matrix-like format requires us to specify exactly what kind of vector we're talking about. So if I'm saying it's an n-dimensional vector, and I'm not saying whether it's a row vector or a column vector, then you don't know which matrix actually represents this vector, because there are two different representations. Because when I'm talking about matrices, I usually have, okay, this is a matrix of the size m times n, m rows and n columns. So that's exactly what I have to specify with the vector. If it's one row and n columns, it's a n-dimensional row vector. If it's n rows and one column, it's n-dimensional column vector. All right. So basically, what I'm saying now is that the multiplication of the matrix by vector, which I was talking before, is also kind of matrix multiplication. I'm just considering the vector as a matrix with either one row, if it's a row vector, or one column, if it's a column vector. So, generally speaking, we can talk about multiplication of matrices, implying that in certain cases, in certain matrices, for certain matrices, it's applicable to vectors as well. Now, the first thing which I would like to do is define the multiplication of matrix by a vector. So that would be actually exactly what transformation of the vectors is, and that's how we started our matrix concept. Well, in a way, I have basically already defined it. When I was writing an equation, actually as many equations as the dimension of the space, but let's do it in n-dimensional case. Let's say we have an n-dimensional vector. In this case, it's a row vector. And let's say we would like to transform it into another n-dimensional vector using a matrix. In this case, the matrix is square matrix, n rows and n columns, because that's how all these equations will look like. Now, this is the first equation. And this is the last equation. That should be U1. So, as you see, the matrix has n rows and n columns, and this is how it looks. Square matrix, the same number of rows and columns. Now, I can multiply it by the vector u, and the vector u is this, as I was saying, and I'm getting the vector v. Okay, so this is basically a general representation of the matrix. Now, let's think about this in slightly shorter format. What is a i's coordinate of the v? Well, i's coordinate from this, it would look like this. I2, U2 plus etc. plus IN, UN. Now, what does it remind you? Well, I can tell you what it reminds me. If I take oops, if I take the ith row of the matrix A, ith row would be here, I1, In, and consider it as a row vector. So I will specify it this way: I star. It's A, I1, A, I2, etc., A, In. Now, this is an ordered set of numbers, and I can always consider it as a row vector. Now, this is a scalar product of row vector A ith, the row vector of the matrix of transformation, and our original vector. So I can say that this is equal to scalar multiplication of the vector, row vector in the ith row of our matrix, and our original vector. So that's what ith coordinate is. So the first coordinate is row vector in the first row, scalarly multiplied by our original vector. The second coordinate of the result is the second row vector of the matrix of transformation, multiplied as a scalar product by our vector, etc. So this is an important note which you really should take into account, because it looks simpler than something like this or something like this, right? Okay, so this is an introduction as a concept of what the product of the square matrix of the size n by n and n-dimensional vector is. What I will do next, I will explain a couple of simple cases of this particular transformation, and it would be clearer to understand how matrix really represents a transformation of the vector space. Okay, so let's go into a couple of examples, and these examples will be in a simple two-dimensional case. So our vectors, which we are transforming, belong to the plane. So they're all two-dimensional vectors. And here's my first example. Let's take the matrix 2 by 2, which looks like this, where k is some number. Doesn't matter what it is, just some real number. And I would like to multiply this by a vector. Now the vector is any vector, u1, u2, and see what happens. Okay, well, if I multiply the square matrix by a vector, I will get another vector. Question is, what kind of this vector is? Well, according to the equations, v1 is equal to k times u1 plus 0 times u2. a11, a12, a11, a12. Now v2 is equal to the second row, 0 times u1 plus k times u2. So this is equal to k u1, this is equal to k u2, and what do we have now? We have that the vector v is equal to k times vector u, right? If you multiply the constant by a vector, you will multiply each component, and that's exactly what vector v actually is. So the matrix of transformation, which is a stretching by the factor of k of an entire vector space, so every vector will be stretched by k. This matrix of transformation is this particular matrix. So this is an example of how the matrix describes the transformation algebraically. So we can talk about stretching our vectors by a factor of k, or we can say that all our vectors are multiplied by this particular matrix according to the matrix multiplication. Okay? Now, a particular case of that, if k is equal to 1, obviously we have no transformation, right? We're multiplying by 1. So the matrix 1, 0, 0, 1 plays in the multiplication lingo the role of unit matrix. It's a multiplication by this particular matrix results in basically no change in the vectors. So this is called the unit matrix. And the usual notation is with the letter I. Okay? Now, let's consider another example. Another example of a linear transformation -1, 0, 0, 1. Okay, so what kind of a transformation this particular matrix represent? Well, let's multiply this by u1, u2. And what do we have? First, we have to multiply the first row by these coefficients, which is v1 is equal to minus u1 plus 0 times u2, and v2 is equal to 0 times u1 plus 1 times u2, which is u2. So what is this particular transformation? Well, let's just consider it this way. If this was a vector u1, u2, it will be transformed into minus u1 and u2. So this is a reflection. It's a reflection relative to the y-axis. It's a linear transformation, obviously, and it's represented by this particular matrix. So this matrix is a reflection. So again, we can talk about reflection, and we can talk about these changes of the coordinate. But at the same time, we can say that exactly the same transformation can, in a matrix format, be represented by a product of this matrix by a vector. All right? Next example, as you, I'm sure, will be very comfortable with. Now this would be plus, this would be minus. Then v1 would be equal to u1, and v2 would be equal to minus u2. So what is this? So u1, this is our vector. u1, u2, so u1 remains intact, but u2 is changing to minus u2. So that would be reflection relative to the x-axis. All right? That's as simple. Okay, another example is this. What do we have here? Well, let's see. v1 is equal to 0 times u1 plus 1 times u2, which is u2. v2 is equal to 1 times u1 plus 0 times u2, which is equal to u1. So v1 is equal to u2, v2 is equal to u1. So what do we have here? So this is u1, this is u2. Now, the new coordinates, the abscissa would be equal to the ordinate, which is this one. This is v1. And the ordinate is equal to abscissa. This is v2. Well, obviously these are symmetrical relative to the bisector of the angle. So we are changing x to y and y to x. That's what basically this is. We are exchanging the coordinates. And in the two-dimensional case, this is a symmetry reflection relative to the bisector of the main angle. And the last example, I am borrowing from the lecture which was dedicated to rotation of the vectors. So if you don't remember, go back to that lecture, but basically what it says is we are talking about this particular equations. So when I was talking about a rotation of the vector by the angle phi, these are the equations which relate new coordinates with an old coordinates, where phi obviously is the angle of rotation. Now, can I specify it in the matrix format? Well, obviously yes, I can. And the specification is, this is the matrix cosine phi minus sine phi, cosine phi. So if I multiply this matrix by this vector, I will get this vector, right? So this matrix specifies the rotation. So basically, look, what we have done right now, we have specified stretching, we have specified reflection, different reflection, and we have specified rotation. Basically, any kind of linear transformation is the combination of these basic transformations. So right now, I think I have completely described how to multiply matrix by a vector. Now, this is just the beginning, and this is related to transformation. Next thing which I would like actually to show is when I specify a couple of transformations consecutive. So from one vector we go using one matrix of transportation to another vector, and then from that vector using another matrix of transportation yet another one, the third vector. Question is whether my matrices can be combined in some way. So let me just jump forward. So if I do this, this is my first transformation of the vector into, let's say, V. And then I have another matrix which is multiplied by this V, and I get W vector. Question is, can I specify it differently? Can I define my matrix multiplication? So at first I multiply the matrices first, just by themselves, and then I apply the resulting matrix to my original vector, and I get whatever I get the first time. Now, what this requires? Now, so far I have defined only the multiplication of matrix by a vector, and this is another matrix by vector again. This is multiplication of matrices, and this is the subject of the next lecture. All right, that's it for today. Thank you very much. I would like to point to Unizor.com as the source not only for these lectures, but also for many different problems solved on this, and also there are some exams for registered students. I also suggest you to get some supervision involved, parents or teachers, whoever, who can enroll students into this or that particular topic, check the exam, and they can mark certain topics as completed and enroll into next topics, etc., which gives the supervisor a control over the educational process. So basically that's it for today. Thanks a lot and good luck.